people think about physics as this very solitary thing. And for Isaac Newton, I'm sure it was. But for most of us these days, it's really not. When I was a kid and I thought about what it was going to be like to do cosmology, I envisioned myself sort of, in a room with a blackboard, by myself contemplating the cosmos. And since the pandemic, that's been more my situation and is not that effective.
I'm Michael Tamblyn, CEO of Rakuten Kobo. We make e-readers and apps, we sell ebooks and audiobooks all over the world, and we do it because we love reading. We want to make reading lives better. One of the best parts of the work that we do is that we get to talk with authors about their books, as well as the books that shaped them as writers and as readers. This is Kobo in Conversation. My guest today is Katie Mack, theoretical cosmologist and the author of the book, The End of Everything, Astrophysically Speaking. It is a surprisingly happy tour of the handful of ways that the universe will likely end, which, as the book explains, are not equally depressing. If you caught our latest Staff Picks episode, you've heard me praising it as one of my favorite books of 2020, and I am so delighted to be speaking with the author. Now, Katie Mack, welcome to Kobo.
Thanks very much for having me.
I first heard you speak about The End of Everything at a Perimeter Institute lecture online right at the beginning of the pandemic. And when the invite hit my inbox, I thought, well, this isn't going to help my current state of mind.
Yeah.
But it did. How has it been for you, essentially on a virtual end of the universe tour during a plague year?
Yeah, it's been really interesting. I think that I obviously I'm bummed that I didn't get to do a real book tour because I'd been kind of looking forward to that. This is my first book, and I thought it'd be fun to go around signing books and things like that. And I didn't get to do that, but I have been able to talk to a much broader range of audiences, and I've been doing a lot of these kind of virtual events. And I've been talking a lot about the end of the universe, and you would think that nobody wants to hear about that when they're already depressed about the world. But I think actually it a lot of people have told me that it helps to think about something so abstract and distant, and there's a bit of kind of catharsis thinking about like, oh, everything's going to be destroyed, when you're so focused on like such a, we're all in these really small spaces right now, right? We're all very confined. A lot of us have been, sort of in the same room for a year. Like, I mean, you get out a little bit when you can, but for a lot of us, our world has just gotten a lot smaller, and being able to kind of separate yourself from that and think about these big, just massive ideas and this unimaginable destruction, like something about that is a little bit comforting in a weird way.
It is. The end of everything almost every time is a very expansive conversation, at least for a while until it's not. Now, I have to make a confession, and this is one of these sort of good news, bad news things. The good news is that people who sell books, like me, we get asked a lot for our favorite books of the year by media and by each other and by family members who are looking for Christmas gift ideas. And this was my favorite nonfiction book of the year for all kinds of reasons. Cool. Oh, yeah. Fascinating topic, perfectly explained, gives a reader a feeling of how amazing it is to work in cosmology. There was just one problem.
Okay.
I constantly stumbled on the name, and this is entirely my fault. Someone would ask, what's your favorite book of the year? And I would come out super strong and say, oh, The End of Every World, Astrophysically Speaking by Katie Mack. Everything, The End of Everything. I would always get there, and I always had the author. And there would just be this moment of lack of confidence, I think, between everything in universe, and people would look at me as if I was brain damaged. So I am out here, pushing this book semi-competently. And if I say the name of the book a lot as we are recording this, it is to atone for all of the other times that I didn't perfectly land it.
That's all right. I've been on a few sort of virtual events where somebody would say, and thanks very much, the Katie Mack, the author of The End of the Universe, and I don't have time to correct them because it's right at the end.
Wait, what?
Oh no, not quite. We had a lot of discussion about the title with the publishers, and part of it was I wanted something kind of pithy, but that we also had to somehow get across that it wasn't. It wasn't metaphorical. We really meant the end of everything very literally.
Full stop.
And yeah, and I didn't want to make it sort of dry, like how the universe is destroyed, or I wanted something that. Anyway, it was a long discussion. It's hard to come up with a title that really portrays. Yes, we are talking about the total destruction of the universe, but also it's not too heavy.
Right.
That's
but
a
in a
hard
good
thing.
way.
Yeah.
You are a cosmologist in your everyday life. And for people listening who don't know the different flavors of physicist, can you describe what that field covers?
Yeah, so cosmology is really the study of the universe as a whole. So in astrophysics, there are a lot of different subfields. You can do astrophysics about galaxies or stars or planets, or particle astrophysics about really high energy events in the universe, and so on and so forth. And cosmology is the study of sort of the evolution of the cosmos itself, the history of the universe, the future of the universe, anything on a really, really big scale where you're talking about either fundamental principles of how the universe works or its past and how it's changed over time. That kind of thing is all part of cosmology.
And it feels like there's a hierarchy. Like, cosmologists are the coolest ones. Like, this is...
I mean, I couldn't possibly argue against that.
Lots of people in the field spend a lot of time focusing on the beginning of everything, which is not what this book is called.
Right.
On the very thin slices of time that make up the very beginning of the universe.
Yeah.
And even in the end of everything, you spend some time orienting us to the Big Bang and cosmic inflation because we need to know about the beginning to talk about the end.
Yeah.
But what can studying the end of things tell us that the beginning can't?
Well, I think, part of it is just that we kind of want to have the whole picture, and you can't do that without covering both sides of that. But also, different ideas about the beginning of the universe do give you different possibilities for the ending, and so they're really tied together. Like, for example, if you're talking about a cyclic universe, one that cycles from beginning to end and back and forth, the ending is part of the beginning of the next cycle, right? And so there are connections there, and just for when you have different ideas about, for example, the dark energy that's causing the universe to expand faster and faster, those will lead to different possibilities for the ending. And so by thinking about what's going to happen in the distant future, it helps you kind of piece together and conceptualize what's happening now and what are the big forces that are governing the cosmos. And so, some of these questions, especially when you get to the weirder stuff like vacuum decay, where it's really connected to particle physics and the fundamental physics of the universe, just asking those questions can really lead you down interesting paths for better understanding the theory.
The book covers 5 different options: heat death, big crunch, big rip, vacuum decay, and the last one you titled the bounce, but it sounds like sounds like you would describe it slightly differently as cyclical.
So it's one of those things that I'm talking about a few different possibilities that all have similar characteristics about some kind of cycle, and a bounce is kind of one of the ways to talk about that.
You have been touring this book and more generally speaking about this field of research for a while now, and there are amazing videos where you describe each of them in detail. But just in case you were getting a bit tired of talking about them, I'm going to try to mix it up for you.
Okay.
So for each of the ends of the universe, I have attempted to summarize it in a haiku. And for each one, you get to assign a grade in terms of its ability to encapsulate the theory And then we can talk a bit about the things that don't fit into 17 syllables. And you get to choose which order we do them in. And you could be harsh. After all, this is yours and a lot of other people's life work here. So they deserve good poems.
Okay.
And you've made it clear from the very beginning of this book that there are no happy endings here. So these are not happy poems. Okay, so now you get to choose which one you would like first.
Okay. Let's start with the Big Crunch. That's a good starting point.
Okay. Big Crunch. After expansion, it crunches back down again. Hope you have sunblock.
That's fantastic. I'm gonna. Gosh, I have to give a grade. Are we doing like A, B, C, that kind of grade?
Yeah.
Ooh, a B plus.
Okay.
I'll say.
Okay.
Yeah.
So when we're talking about Big Crunch, what are some of the main principles we want to make sure we understand?
The main idea behind the Big Crunch is just that you take the current expansion of the universe and reverse it. So right now we know that the universe is expanding, galaxies are getting farther away from each other. Just dial that back, turn that around, and you get a Big Crunch. You get everything's coming together, and it all ends in fire. You end up with all of the radiation, all the cosmic radiation gets compressed and incinerates everything, and that's you have a wonderful allusion to that with the sunblock in the poem. Very good. You do need something more powerful than that, because you're not just dealing with UV. You've got gamma rays. You've got a huge sort of space full of plasma. So it gets pretty bad, but yeah, that's the Big Crunch.
That was the part that was most interesting to me, is that it's not just the matter that's floating around out there. It is all of the radiation that has ever been given out. Everything comes back down.
Yeah. And as the universe is compressing, all that radiation is being hardened. It's being driven up in frequency, and therefore getting more powerful and more dangerous. So just the way that UV radiation is more harmful than visible light for us. If you take all the visible light in the universe and you compress it, you're going to get harder and harder radiation, UV, X-ray, gamma ray. And so as you evolve toward the Big Crunch, you're getting into this more and more dangerous radiation environment, and space is just getting brighter and brighter and hotter. And eventually the sort of crescendo is that you get to the point where there's so much hard radiation in so-called empty space that it starts to ignite the surfaces of stars. You get thermonuclear explosions across the surfaces of stars, and that's just this fantastic image.
Big finish. Okay, next one. All
right. Let's do the Big Rip. This is a fun one.
Okay.
Actually, wait. Sorry. No, let's do the heat death. I want to go in order because it's a little bit easier to explain. Let's do the heat death.
Okay,
first.
heat death.
Yeah.
Dark energies push until expansion slows down. We're cold and alone.
Ooh, I have to give that one a C.
Okay.
Because the expansion doesn't slow down. It keeps speeding up. It's not that the expansion slows down. It's that there's just nothing left to do.
Okay. Got it. Yes.
Yeah.
Okay.
Yeah. So the way that the heat death works is that you just have more and more expansion, and the expansion goes faster and faster, but eventually everything is so separated, all the distant galaxies are so distant that there's kind of nothing left. And everything else slows down because there are no more kind of processes in the universe, everything kind of fades away and decays, and the universe is left cold and dark and empty.
All right. Really, you were generous with the C. I'm assuming you're grading on a curve. Okay, that's by far the saddest one.
That is the saddest one, yes.
Which is one of the things you talk about through the book is you kind of do give a bit of the emotion of each one of these. Some of them are, big and sudden and, and abrupt, but this one is definitely the long goodbye.
Yeah. And it's funny too, because it's also the one that's apparently, based on our current understanding, the most likely. At least it doesn't require any new ideas. It seems to be, if you just extrapolate what's happening now, you get to a heat death. And that makes a lot of people really sad. When there was a quote I took from one of my colleagues in the book, Herania Pires, who was talking about how sometimes she gives talks about this and people cry, right? Like people get really sad.
I totally understand that.
About the idea that the universe is just going to fade away and everything's going to just decay into, this kind of waste heat of creation, and there will be nothing left.
All right, next one.
Mm-hmm. Let's go big rip.
Okay. Bonds that make matter need a cosmological constant or stuff breaks.
Ooh, I like that. That's good. I'll give that an A minus. That's nice. Yeah. So that's making reference to the fact that in a heat death scenario, dark energy, the stuff that's making the universe expand faster, is a cosmological constant. It's just a sort of property of the universe that you get this expansion. And a nice thing about a cosmological constant is that it doesn't tear things apart. It just kind of makes more space, moves things around, but doesn't actually mess with, individual galaxies or stars or planets or anything like that. But if you have a more powerful kind of dark energy called phantom dark energy, that can actually destroy stuff. So, when we talk about the universe is expanding, generally we just mean that, galaxies are getting farther apart. We don't mean like this room is expanding or anything like that. But with a phantom dark energy kind of expansion, you would eventually get that this room is expanding. It's something that sort of, there's this expansive force that builds up within objects and destroys them from within. And so you'd get, first the galaxy clusters would be pulled apart, and then galaxies, and then solar systems, and then planets and stars, and then eventually atoms themselves are sort of ripped apart by this ever increasing dark energy. And that's the big rip.
It's by far the hardest one. First, because it's really hard to make a haiku with the words cosmological constant. There's a lot of syllables. Yes. And it's also virtually impossible to fit phantom dark energy into a haiku. It's yeah.
Yeah. No, that was a very good effort. I appreciate that. Yeah.
Okay.
Yeah. Okay. So next we have we got to do vacuum decay, right?
All right. There is a lot of work that went into this one. So I made 4 different tries, and you can choose.
Okay.
Thought physics was stable. False vacuum jumps to true by standard model.
Ooh, that's good.
Okay, that's number 1.
I like that one. Okay.
Number 2. False vacuum until universe says, hold my beer. Then weirdness ensues.
All right.
Okay.
All right.
Number 3. Who suspected that quantum tunneling could ruin your day? And then finally,
nice. Yeah.
If the Higgs field says, I might have a midlife crisis, we're all kind of screwed.
I like all of them. I'm giving them all.
That's
an
all
A.
I got for vacuum decay.
Those are great. Those are great. A for all of them. They're fantastic. Yeah. No. Those and they really, you get across every little piece of that story in a different haiku. I like that. Yeah. So the idea behind vacuum decay, of course, is that the universe might not be stable. It might have this kind of flaw built into it where a quantum tunneling event, a sort of random quantum process at a subatomic level at one point in the universe, could occur that would create a bubble of a new kind of space, and that's called a true vacuum. That would mean that our space, the space we live in, is a false vacuum, and then there would be this true vacuum bubble, and that would just randomly form somewhere in space and expand out and destroy everything. And it's a particularly intriguing possibility because it's totally unpredictable. A quantum tunneling event cannot be predicted. It could happen at any moment. You can put probabilities on how long it would take before it occurred. So there's sort of a lifetime that you can estimate for the cosmos in this scenario, and you get a number like 10 to the power of 100. So, a very long time from now. But we can't say for certain. That's all probability. So it's sort of my favorite possibility because it is so random, and because you can have such a tiny thing, a subatomic event, that could end up destroying the entire universe.
And is that quantum tunneling event the only kind of event that could precipitate this, or is there any other way that we could get from the false vacuum state that we're potentially in right now to the true vacuum state where everything ends?
So in principle, if you have a really high energy event that can perturb what's called the Higgs field. So the Higgs field is this sort of energy field that pervades all of space. You might have heard of the Higgs boson, this particle that was discovered at the Large Hadron Collider. The Higgs field is connected to that particle. And the Higgs field kind of determines the laws of physics in our universe for particle physics. And so in principle, if you can find a way to excite that field, which means just kind of move the energy around in that field in a certain way, then you could create another, a bubble of true vacuum. But as far as we know, that's not really possible to do, with like particle collisions or something like that. There have been a lot of really high energy particle collisions in the universe through, just cosmic events, and none of them have set off this vacuum decay. And it looks like from sort of the theoretical side, it would be a very hard thing to make that happen other than a quantum tunneling event. So probably if it can happen at all, then it would be from this just random thing that would happen somewhere in the cosmos. And we don't know for sure if that's really possible, because there's a lot of the theory that we're still trying to figure out. But if it is, then it could technically happen at any moment, but probably would not happen for a very, very, very long time.
And one of the points you raise in the chapter is, especially at the very beginning of the universe, we had a lot of very high energy events going on. So if high energy events were one of the things that was going to kick this off, there have been opportunities in the past that really haven't been taken up.
Yeah, exactly. And some people worried about things like the Large Hadron Collider, particle colliders causing vacuum decay. Like that was something that people have at various times kind of panicked about. And, just to be clear, anything that we can do in terms of colliding particles on Earth has been done at much higher energies, billions and trillions of times by the cosmos itself, and none of those have set off anything like this. So, what we can do here on Earth is really not anywhere close to doing anything that would affect the Higgs field. So, that is not a thing to worry about.
But is it safe to say that this is your favorite one?
Oh, yeah. yeah, for a number of reasons. I mean, one, because you are connecting subatomic physics to the destruction of the entire cosmos, which I think is just a cool idea. As a physicist, that's exciting to me.
That's just a good time.
Yeah. And then also because it's so random, like it's this sort of Damocles like hanging over the cosmos. I think that's a fun idea. And then also, it would be very quick and painless. This bubble of true vacuum when it forms, it would expand out. It would expand out at about the speed of light, so you wouldn't see it coming, because by the time you see the light from it, it is on top of you, and you wouldn't feel it when it hit you because it's traveling much faster than your nerve impulses, right? So you don't get a message from when you start to be disintegrated by it, your brain doesn't notice. And then there's no tragic aftermath, nobody's going to miss you. It's just, everything's done. It's just clean and over and finished. So I don't know, that kind of appeals to me. It's very neat.
Clean. Mm-hmm. For the last one, yes. For the listeners, we should do a bit of a nomenclature check. When we're talking about brains in the context of a cyclical universe, what are we talking about?
Yes. So a brain, BRANE, sort of short for membrane, is a kind of surface or a kind of space that has a certain number of dimensions. So right, like we have 3 dimensions in our everyday life. A piece of paper is roughly 2-dimensional, although it does have a little bit of a 3rd dimension in it. And it's possible that our universe, these 3 dimensions of space, might live in a higher dimensional space. So there might be another spatial dimension that we can't perceive that goes in some other direction. And so our universe might be a 3-dimensional brain, sort of surface in a 4 spatial dimensional space. So it gets a little complicated because when we talk about dimensions in physics, we often talk about time as the 4th dimension. But when we just talk about spatial dimensions, dimensions you can move around in or whatever, we have 3, and we could live in a space that has more, and then we could be a 3-dimensional, 3 spatial dimensional brain in that higher space.
Okay, so based on that, here's my shot for cyclical universe ending.
Okay.
Maybe brains touching keeps the Big Bang rebanging. Ekpyrotic spark.
Nice. Yeah, I got to give that one an A as well. That's fantastic. Yeah. So that's referring to the ekpyrotic model of the universe, which is this idea that it's a cyclic cosmology where you have a contracting universe that then hits a new Big Bang and then expands and then contracts again, and you get a new Big Bang. And that's really where the term bounce kind of comes from, that bouncing from the contraction to the expansion phase. But in the first version of the ekpyrotic universe that was proposed, the idea was that contraction, that bounce, was actually 2 parallel brains in a higher dimensional space kind of hitting each other and bouncing off. And so as the brains are kind of coming together, you have this contraction, then you have the bounce where they literally sort of bounce off each other, and then they expand in their own space. And sort of new versions of ekpyrotic universe don't require these extra brains, and you have it's governed by other kinds of physics. But I really like the imagery of these higher dimensional spaces coming in and colliding with each other, where we could be sitting on this brain here and we don't even know that there's a whole other universe, like parallel universe, right next to us that's coming toward us, and it's going to hit us and spark a new Big Bang and destroy the cosmos. So that's another sort of out of nowhere literally out of this other space kind of ending of the universe.
This model, in terms of the genesis of the book, kind of got added at the last minute. This is sort of the physics equivalent of late-breaking news.
Oh, yeah. So what happened was one of the originators of the ekpyrotic model was my PhD advisor, Paul Steinhardt at Princeton. And so I was writing up the ekpyrotic part of this chapter, and going through the thing with the brains and everything, and I sent him an email to ask about just if there are any updates and if I got the physics right. And he said, actually, we have a new model that came out a month ago that totally rewrites this whole picture. And so I ended up having a couple of phone conversations with him and going through, it was during the time I was writing the book, right up until I was turning in my final draft, there were these new developments in that model and totally rewriting the mechanism that this whole thing was based on. And so it was a bit of a challenge to then say, okay, I need to start from scratch on this chapter and really rewrite everything and try and get this put together properly, because he was my PhD advisor. I don't want to insult his model in any way. I want to properly represent what he's done, and I want to get the latest physics in there. But it was definitely very, very close up to the wire revision.
And it helps to make clear that this is all still very much emerging and active science. None of this is settled right now.
Yeah, absolutely. I mean, there were other aspects of that came in right at the last minute. Like there's another bouncing cosmology example that I put in there that has to do with a sort of previous anti-universe that becomes our universe through this transition at the Big Bang. That was only published a few months before I had to turn in my draft. And then some of the ideas around vacuum decay were very, very new. I was reading papers that were published within weeks of when I was writing that book. It is all very new and very actively changing and emerging, and especially the chapter about how we're going to figure this out. What is the future of this area of study? That was all talking about telescopes that are being built right now and surveys that are going around right now and new discoveries and things that we're going to launch into space in the next couple of years. It's all really actively changing all the time. And that's part of what makes it so interesting and exciting, is that this is a really great time to learn about the end of the universe and the science of it, because there are so many developments coming up and we're learning so much.
You are always very careful and generous in this book to let us know whose research has contributed to each of these theories. Of the five, which are the ones that felt most squarely in your wheelhouse in terms of your field of study, and which ones were opportunities to dig into someone else's field of research or someone else's area of investigation?
So the only one that I have actively written papers about, and that papers being one paper at this point, is vacuum decay. So and really I started very much digging into vacuum decay because I was already thinking about the book and I was already kind of interested in this idea. But the other topics, my area of research mainly is dark matter. Mm-hmm. Well, dark matter and the early universe. And I do talk about dark matter in the book. It a couple of times. It's, this invisible stuff that holds galaxies together. We don't know what it's made of. And I talk about the early universe a lot in one of the chapters where I'm sort of walking us through where we are and where we're going. But the star of the end of the universe story is really dark energy, and I've never written a paper about that. That's a little bit outside my usual wheelhouse, because the observational side is all about sort of mapping galaxies and stuff, and I don't do observational work. And then the theory side, a lot of that is sort of deep quantum field theory stuff that I haven't worked on either. So there was a lot that I was learning in terms of the really fundamental research behind these topics. But it's also true that that because of the field I work in, early universe theory and cosmology, and I've worked on sort of galaxy formation and stuff like that. All of these topics kind of are very connected to the work I do. So, understanding how the heat death works and how the Big Rip works, and all of these things are very much things that I've come through in my own studies and in my own research, even if I haven't been actively contributing to those fields.
You are a researcher who has this major presence in talking to non-science people about science. Through Twitter, you're on Astro Katie, on YouTube, in lectures, and now in this book. If you were to look at your time spent, what's the percentage of time look like right now between research, talking about the end of everything, and then the other general public-facing, let me help you understand science better, and then the rest of your life?
Yeah, well, it's a bit skewed right now because I've been doing a lot of book stuff and book promotion in the last year, and so that's kind of changed the balance quite a bit. But officially my time, according to my faculty responsibilities, agreed with my university, all of that, is somewhere around a third of each of research, teaching, and outreach. So I maybe a little bit more on the research and outreach part and a little bit less on the teaching part. So I've maybe something more like, kind of research and outreach are similar in terms of the slice of time, and then teaching is a bit less. And that's been a nice balance that I've been able to set up with my university, so that I do have more time to both stay engaged in my research and really, move that forward and supervise students and, go to conferences and all of the kinds of things you have to do as a researcher. So I really do have time to do that, and also have this big public facing side, and also do the teaching responsibilities my department needs, and so it's it's still kind of a difficult balance sometimes. I still have it's not always easy to juggle everything. But I think that it's a good sort of weighting of all the things I like to do. And yeah, so right now I think I'm putting more time into the public side than usual because of the book. But then this next semester I'm going to be sort of shifting back more into research being the main thing.
Okay, so if your dean is listening, like, we're checking all the boxes here. It's all
Yeah.
it's all good.
Yeah.
Every once in a while, in the end of everything, you hint at the math behind the theories, and I think a couple of times you even say, if I had more time, I would take you into some of the really beautiful equations that describe this.
Yeah.
They say that talking about music is like dancing about architecture. How different is the experience of thinking and talking about these ideas when you can get at the math behind them?
It's funny. A lot of physicists I work with have a very sort of intuitive connection to the mathematics in the sense that, if I'm talking to them about some physics concept, like, the first thing they'll do is write down the equations, and then that's what really makes it clear to them. And I'm a little bit different on that regard. Like, I do get something out of the equations, and if I understand the concept, the equations are meaningful to me. But I think more in terms of the sort of physical concepts and sort of imagery, I guess. And so for me, if I have a really good intuitive analogy, if I can visualize what's going on, that helps me interpret the equations, that helps bring the physics to life for me. And so I think that's one of the things that helps me with writing books like this, or explaining things to the public, which is that, like, for me, I need to understand it at a really deep level that isn't mathematical in order to get something out of it and in order to work with it. And so I don't assume that I can just write down the equation and then you'll get it. For me, the mathematics can be really important and helpful, but for the concepts, I usually come out about it in a different direction. But there are cases where if I could give you the mathematics, then I could get across an idea that I can't do in words. So there are certain things about, like, talking about symmetries and things like that, where if you could look at the equation and really understand the equation, then it would make sense to you in a way that there really isn't a good analogy. There isn't a good sort of conceptual thing. It's just a mathematical principle, and those things are the hardest things to get across in words.
So then we just have to convince the publisher to do, like, an extended dance mix of the book with all of the math.
Yeah.
When did the idea to write this come along?
It was a few years ago. So I started thinking about a book in the abstract before I started thinking about this book. And what it was I was thinking about writing a book and talking with some agents and publishers, and at first I thought I might write a book about dark matter because that's what I usually work on. But then I realized that when I give talks to, public audiences, at planetariums or whatever, one of the things that people get most excited about is the end of the universe. And I also realized that over the years, whenever I've had a chance to talk about one of these weird end of universe scenarios, I really jump at it. So, when I was in grad school, we had to do this, graduate seminar thing, and I did my talk about the Big Rip. And then when I was a postdoc, I went to some talks about vacuum decay, and then I was doing a public talk about something, and I managed to use vacuum decay as an analogy for something about seizing the day or whatever. And I had a lot of fun sort of throwing that in there. And I just realized that some of these topics are not only really interesting to me, but also things that the public responds to. That an audience gets kind of excited about the idea of the universe tearing itself apart.
Right. And so it was literally, live every day to its fullest because ekpyrotic disaster is just around the corner.
Sure, yeah, that kind of thing, or vacuum decay, like you never know what's going to happen next. So, like it could come at any moment. Just have fun. Yeah. And so I realized that these are really fun things to talk about. And also I realized that the research I've done and the education I've had really makes me kind of the right person to write this story, because I've worked in enough of these areas, and I have the expertise, and also, I'm it's something I'm really excited about, and I know all the right people to talk to about each of the topics, and it just all fell together as like this is the book that I should write right now. This is something I'm gonna have fun with. I'm gonna be able to put in all of my favorite cosmology facts, all my favorite little jokes, and shove a lot of other things into the footnotes, and this will be fun for me, and it's a topic that isn't really discussed as much in the popular press. There are a lot of books about the beginning of the universe, and really not that many about the end, and so it was an opportunity to dig into something that was not talked about enough, and could be really, really fun.
Were there any authors who were in the back of your mind when you started thinking about writing a science book for a popular audience?
I mean, I thought a lot about A Brief History of Time, because that's the book that I first read to start thinking about cosmology when I was basically a kid. I think I must have read that when I was about 10 years old. So that was a book that came to mind a lot, and in interesting ways. So one of the ways it came to mind is that that it was a really sort of elegant discussion of a lot of deep topics. Another thing that I thought about when I thought about that book is the fact that it's got this reputation as being one of the most bought but least read books in history, right?
Mm-hmm.
So, and a lot of people found it just, beautiful but incomprehensible. And so I really wanted my book to be something that people would buy and read, and that it would be a book that could be understood and wasn't just this beautiful, elegant thing, but was actually accessible and actually comprehensible to the general public, and not just to people who were already sort of deep in this field. So I thought a lot about that book, sort of both as an aspiration and as a cautionary tale, in some ways. But in terms of other books, like I don't read much nonfiction. Most of what I read is sci-fi. So I spend a lot of time reading science fiction, occasionally other kinds of sort of literary fiction. I reread the Jane Austen novels a lot. There's my sort of literary diet is not science, is not nonfiction, and I think there are a couple of reasons for that. It's hard for me to read a popular science book that's anywhere near my area of expertise, or even outside it, really, because it's hard. I spend a lot of time kind of back translating to the technical version. So if I'm reading if I'm reading a book about, black holes, and they say something about, imagine that this fabric of space is this curved, sheet or something, like I'm reading that and I'm thinking, okay, they're talking about the curvature, and they're, these are the equations that they're referencing, but they're not actually saying that, but this is what they mean. And so it's like a lot of extra work for my brain. and I tend to, and it tends to be at a level where I already kind of know the content. And so it's just not that much fun for me to read books like that generally. And so what is fun for me is to read about spaceships and to read about time travel and, future societies and all of that. I find that really good for escapism, for just like getting me out of my head and, being in a totally different mindset. So I read a ton of stuff that just, kind of takes me away from my daily life.
Okay, as a bookseller, I think I get fired if I don't ask you for science fiction titles that you have really grabbed you lately.
Oh, gosh, there's so many things. So some of my favorite authors right now in science fiction are, let's see. Oh gosh, I'm just gonna blank on everybody's name suddenly.
I should have primed you up ahead of time.
Yeah, you should warn me. So Martha Wells, Becky Chambers, Anne Leckie. Let's see. Who's the author who wrote
Murderbot and Ancillary Justice?
Oh gosh.
Yeah.
Fantastic. And then the fifth season, N.K. Jemisin. I just read a lovely debut novel called Winter's Orbit by Everina Maxwell. That was a really great book. I just read Kim Stanley Robinson's latest Ministry for the Future. Mm-hmm. That was really good. Sort of, that's a lot closer to nonfiction than I usually go. Actually, his stuff is very, very sort of hard science. So that was great. I just read. I've been reading a lot of John Scalzi's stuff. His stuff is always a lot of fun. Chuck Wendig, Wanderers is an amazing novel. Gosh, I could go on for a very long time. But
that was great. My bookselling mission has now been fulfilled.
Okay, excellent.
Isaac Newton famously did some of his most foundational work during the year when the Black Death was ravaging London. For you and for your colleagues in theoretical physics, has this been a productive time?
I think for a lot of us, it's not been very productive at all. A lot of my colleagues have, have children at home, and when they can't go to school, like it's just that extra childcare responsibility that makes it impossible to do anything. Mm-hmm. So there's been, that's a lot of what a lot of people have been facing during the pandemic. Just the disruption at home. So I don't have that going on, but I know that's been a challenge for a lot of people. It's also, people think about physics as this very solitary thing. And for Isaac Newton, I'm sure it was. But for most of us these days, it's really not. When I thought about being a physicist, when I was a kid and I thought about what it was going to be like to do cosmology, I envisioned myself sort of, in a room with a blackboard, by myself contemplating the cosmos. And since the pandemic, that's been more my situation, and it is not that effective. So, it is, I work much better when I can go and talk to people, when I can attend conferences and go to seminars and share ideas and have the morning coffee discussion about new papers that have come out. That kind of collaboration is like, that's what makes me a more effective researcher. And we try to to simulate that online. There's a lot of Zoom meetings. I have meetings with my students and my colleagues, and we do online conferences, but it's just not as good. And I also find that going to the office was actually really helpful for me for like focus, and going to a cafe to like take some papers with me and go sit in a cafe and read a bunch of papers, drink some tea, collect my thoughts. Like not being able to do that is a little bit harder as well. When I'm just in one room all the time in my apartment, that's just, I don't think as well. The way that I work is much better in collaboration, in conversation, and so I've found it a lot less easy. And then also it hasn't been so much an issue for me, but a lot of my colleagues also are doing their teaching online, and that takes a lot more time than teaching in a classroom. Right. Just putting together videos and online lessons and stuff like that. So there are a lot of ways that it's really disrupted the astrophysics and physics communities.
I've talked to people about this last year as being the time when introverts have discovered the limits of their introversion. And it turns out we actually do need people, and we need people more than we thought.
Yeah. Yeah. I mean, I don't know. I'm a little bit extroverted for a physicist, maybe. But I need to be somewhat around people. I find that I don't work well in a quiet room by myself. Even when I'm when I'm at work, sometimes I'll leave my office and go off to the coffee shop or the library or something where there are other people around, just because that sort of energy is helpful for me.
But you did just become a pilot.
Yes. Yeah.
Was that your pandemic project?
Pretty much. I mean, I think what happened there was, I had just moved to Massachusetts to sort of wait out the pandemic, and I'm in this lovely area in Amherst where there's lots of woods, and I can go on hikes, and I can go running through the forests and stuff, and so I was trying to do stuff like that, but mostly I was just in a room. Right. And I think that the isolation kind of got to me, and I saw that there was a little airport nearby that did flight lessons. And it's something I'd been kind of thinking about in the back of my mind for a very long time, that, it would be neat to just try that out, see about learning to fly airplanes. And, I had no other hobbies. I had a lot of, potentially I had some time. I mean, you never have free time when you're an academic, but, I didn't have anything else going on in my life. And so I thought, well, this is the time to try it out, to see how it goes. And so I signed up for an intro lesson, and then I just kept going back and realized that, I was suddenly totally obsessed with aviation. And so I went through the whole thing. I got my private pilot license, I guess about 2 weeks ago. And I'm gonna go on for more training, and I'm kind of excited to see where that takes me. I'm scheduled to go for a flight this afternoon, so it's I'm doing a lot of that.
We'll let you get to it then. Katie, thank you so much for joining us.
Thanks so much for having me. This was a lot of fun, and thank you for the haikus. They were excellent.
I have been speaking with Katie Mack, author of The End of Everything, Astrophysically Speaking. Find it and the other books we've been talking about, along with previous episodes of the show, at kobo.com/conversation, or click through to the show notes. Make sure to catch every conversation by subscribing wherever you listen, and leave us a review because it helps other readers find us. Kobo in Conversation is produced by Nathan Maharaj and hosted by me, Michael Tamblyn. Thank you for listening.